Hello, in this video we begin to introduce the topic of probability. It's one of the most, realistic and very important and relevant topics in math. So if you've ever played any sort of a board game and you've talked about rolling a dice, so I have a die here rather. If you talked about flipping a coin and saying what's the likelihood that it comes up heads or tails, if you've talked about playing poker and trying to figure out what's the probability that you get a royal flush, right? All of these answers can be discussed and described with theoretical and empirical probability. So if you have your cards, if you have your dice, and if you have your coins, even if you don't, let's get ready to dive into probability. So I want to begin with some definitions. When I'm talking about probability, most of the time you're thinking of theoretical probability. So when someone says to you, the probability that if you have a child, that it'll be a boy or a girl, and it's 50%, let's say, they're referring to this type of probability, this theoretical type of probability, okay? On the other hand, when we are talking about experimental, sometimes the other word they use for it is empirical, right? What we're referring to, you can see it in this box here, is repeating an experiment over and over again and observing the outcomes. What results do I get? So in the case, for example, of flipping a coin over and over again, if you keep flipping and flipping and flipping, you're going to get slightly different numbers, aren't you? Like if you flip for 100 times versus 1,000 times, if you only flip 2 times, right? You're going to get slightly different results when you keep track of the number of heads versus the number of tails. So what do I mean by probability in this case? Probability of an event. And just so you can see here clearly, the way we usually write the probability notation is capital P. We open a parentheses, and inside here, we'll put whatever the event is called, and that's what you see happening right here, probability of an event, okay? So for example, if I want to find the probability of getting a heads, I might write it like this, capital P and then parentheses heads. So that means I'm flipping a coin 1 time, and I want to know how likely it is to get a heads. Now in theory, the answer you probably know, it's 50%. We'll talk about why that is in a moment. But if you were doing an experiment, what you would be looking at is the past. How many times was this coin flipped, and what were the results, okay? So once you figure that out, how many times was the coin flipped, that's the total number of trials that goes in your denominator. The number of times that the event actually occurred in your favor, so the number of favorable outcomes, if you will, that would be what is your numerator. So favorable times on top, total trial attempts on the bottom, okay? So let's take a look at this example. Suppose you tossed a fair coin, and when we say fair, we mean that you have an equal likelihood of randomly getting one side or the other, heads or tails. It's not weighted in any way, and it doesn't have tails on both sides, right? It's not a trick coin. So if you have a fair coin, and you toss it 100 times, so you have nothing better to do but toss a coin 100 times, and what your results give you is 52 times you end up getting a heads, okay? So in this case, with that information, you could calculate the probability of getting a heads empirically or from this experiment. And that would be 52, that was the number of favorable outcomes, over the total number of attempts or trials, 100. Now, this could be how you leave your answer. A lot of times, though, people prefer to write probability as a percentage, and percent comes from the word out of 100, right? It comes from that Latin base. So when we're talking about 52 out of 100, that's really easy to make a percent. That's 52%. Okay, so 52% of the time in this experiment, we got a heads. Now that's different than the theoretical answer, which should be 50%, right? We're going to talk more about that in a moment. Another way that you can write probability on your own when you're doing your homework is as a decimal. And again, out of 100 is really easy to make a decimal. That's 52 hundredths, right, or 0.52. You could have also typed it into your calculator, and they would give you 0.52. And then one other thing I want to mention, if for some reason in your homework you're asked to give probability as a fraction, they always assume that you are reducing your fraction. So even though 52 out of 100 is a valid answer, and it's very helpful for getting the decimal and the percent in this case, if you were to try to write this as your final answer, you might be prompted by your homework software to keep trying to reduce. So when you keep trying to reduce, you could divide them both by 2, you could divide them both by 4, the numerator and the denominator, that is. Eventually, you should end up with 13 out of 25. That's right. Okay. So that would be the answer that you would write as a fraction, the reduced fraction. Okay. So what I wanted to show you real quick is the definition of a theoretical probability, which we already talked about a little bit, is the probability of the event is the number of favorable outcomes, okay, And this should really have the word possible, okay? How many favorable outcomes are possible? So when you're talking about flipping the coin, there's two sides of a fair coin, right? A heads and a tails. So how many favorable outcomes would give me a heads? Just one. Divide that by the total number of possible outcomes. What would that be? That would be 2, right? 2 possible outcomes. So it's not always going to be 2, and it's not always going to be 1 in the numerator. It's depending on the situation, or in other words, depending on the event in question. What are we talking about? We're flipping a coin and hoping for a heads. So you could write 1/2, you could write 50%, which is 1 divided by 2, right? Or you could write 0.5, 0.50. These are all the same thing. So always check how your answer is supposed to be left when you're dealing with a homework problem or a test problem, right? But what I'd like to show you is this idea that as you continue to increase the number of trials, as your trials grow, and you have a certain theoretical probability that you already know about for an event, your experimental or your empirical probability should get closer and closer to that, okay, to that probability. So let's go ahead and take a look here, if I can, at this website. You can actually click on it from your interactive notes at home. Flip a coin, I think .fun is what I'm looking at here. Let's see if I can come over. Okay, I think you can see it. And it has a lot of advertisements, so ignore those for now. But what I wanted to show you here was how they allow you to flip a coin, and you can actually flip multiple coins at the same time. You can see above here how you can pick all the number of coins that you'd like to flip. I'm just going to pick one coin right now, and let's say that we flip the coin. You can pick how many times you want to flip it. Let's say we flip the coin 50 times here. Let's see if I can type 50. Oops, erase that. Okay, it only wants me to do it for 5 times right now. We'll just obey what they say. So if I do it for 5 times, it'll give me my results here. Heads, tails, heads, heads, heads. So this was the result of their randomized flip. In other words, if you look at the stats, you can't really see them too well. Let me see if I can zoom that in for you. Control+. The stats that are generated here, 4 heads and 1 tail. But what's kind of neat about this site is if you continue to increase the number of flips that you do, let's see if it lets me do it this time. There we go. How about, just a little bit slow there. Okay, so if we do 111 flips here, I don't want to look through all of those, but I'm going to go to the stats real quick and see what they tell me. So in this case, now we have 58 heads and 53 tails. Okay, so that's getting closer to that even amount, right? And if you continue to ask it to flip larger and larger amounts of coin flips, right, you're going to end up getting closer and closer to a 50-50 scenario, because there was, again, in theory, a 1 out of 2 theoretical probability for each one. So the larger your sample, this is a good statistics lesson, we'll talk more about that in the future, the larger the sample, the closer your experimental probability should get to your theoretical, okay? And if you are curious, you can also check out, I think they have it on this screen here. Yes, at the bottom here, they have a roll of a dice option, and I won't go through it right now, but you can actually do the same thing with dice. You can ask it to roll 1 die, 2 dice, and you can talk about, again, what happens as you do this over and over again, what happens to your empirical versus your theoretical probability. So it's a very nice way to actually practice these ideas, play with them without having to literally roll a die or flip a coin. So I encourage you to check that out if you want to. There's lots of other websites like this if you look for simulations of coin flips. Okay, so with that information in mind, let's head to our first example, shall we? So here's another real-life example. This is from your professor's actual statistics of teaching at her college. So in the first 2 years of teaching at her current college, she gave the following grades. 114 people withdrew, 93 people earned an F, 108 people earned a D, 203 people earned a C, 165 people earned a B, and 94 students earned an A. Okay, so these were the data from my first 2 years of teaching at my current college. Based on these previous results, could we find the probability that a current student, maybe that's you, right, that a current student in one of her classes will receive an A? Now, again, what kind of probability am I talking about here? Am I asking you to calculate the theoretical probability, or am I asking you to calculate the empirical, also known as the experimental probability? So that's the question I have for you right now. Pause the video, feel free to go back to your notes and see if you know the answer. Which is it? That's right. I'm actually interested in experimental in this case, since I'm giving you data about the past to inform you about the future probability. So if I had not given you this data, if I had just said, what's the probability that someone gets an A in my class? Well, how many grades are there? A, B, C, D, F, and in my college, W. So if there are 6 possible outcomes, what's the number of ways that you can get an A? Well, that's one of those outcomes. And so you could calculate 1 over 6 and get your result, right? That would be the theoretical probability of getting an A, right? But what would be the experimental probability here? What would I have to do to calculate the experimental probability of getting an A? If you said, well, I need to know how many people got an A, that's true. That would be my numerator. That's the number of people who earned an A in the first 2 years of my teaching at that college, right? But what would I need in the denominator? If you said the total number of grades that I gave, that would be correct. So if you add up 114 plus 93 Fs plus 108 Ds plus 203 Cs plus 165 Bs plus 94 As, what does that give you? Feel free to pause and then tell me your answer. What did you get? Yep, I got 777. Good job. So technically, that would be your fraction answer, and if you can reduce, you always try to, otherwise you leave it there. But when you put this in your calculator, you're going to be getting some nice decimals, something like 0.1209781, blah, blah, blah. It continues on and on. So for rounding purposes, usually if you're talking about percentages, which usually is what students care most about in this situation, you would really just move your decimal 2 places to the right. So you'd be talking about 12 point something %, and then the 9 is bigger than 5, so we round the number above. So that would be 12.1% roughly. So more than 12% chance of getting an A, right? And then you could compare that. Is that better than the theoretical likelihood if she just picked a letter grade out of a hat? So if I had in my hat an A, a B, a C, a D, an F, and a W piece of paper, and I picked it out, would that have been a better probability for you? Check it out. Go ahead and type in 1 divided by 6 in your calculator and see which number is bigger, right? Okay, so this is an example again of how experimental probability, if I continue to add more data and let it grow and grow and grow, it should tend to get closer and closer to the theoretical probability, assuming that there is no bias of any type or external factors, assuming randomness, if you will. Okay, which is not quite accurate when you're talking about students, but there's a little bit more level of complexity there. Well, let's head over to another example here and also some more definitions for us. So there are some fun facts that we need to know about probability. For example, did you know that the probability of an event will always be between 0 and 1 inclusively? Now that's a lot of fancy mumbo jumbo, but what does it mean? Well, what it's saying here is you can't have negative probability. So if you're sure that something cannot happen, right? If you live in the state that I live in, like Florida, I can tell you with confidence that it's not going to snow tomorrow, right? So I would say the probability that it will snow tomorrow in Florida is 0. Okay? We can't go below 0 for probability. We can't say it's negative 55% or negative 1/2 or something like that. No negative probabilities, okay? What else am I saying? Well, I'm also telling you if the probability of something that can never happen is 0, then the probability that something will definitely happen with certainty is 1 or 100%. You can't go beyond that. So I know sometimes you probably hear people say, you know, I am 250% confident that this is going to happen, right? That doesn't make any sense, right? The most certainty we can ever guarantee when we're talking about probability is 100% certainty. That's what we mean between 0 and 1. No negative probabilities, nothing bigger than 1 or 100%. What else do we know? Well, we just mentioned it. If we know an event is guaranteed to happen with mathematical certainty, then we would say its probability is a 1. It must occur. And if it cannot occur, if it is completely mathematically impossible in real life for this event to occur, we would say the probability is a 0. So again, 1 and 0 are the two extremes. Something else that's an interesting word, we've heard it in previous topics, we've talked about this word, and the word is complementary. And that word, again, is telling us that two things are completing each other, right, to add up to the total. So when we're talking about two what we call mutually exclusive events, another word for that from our set theory chapters was disjoint. If you think back to your Venn diagrams when the two circles had nothing in common, right? So if these are two mutually exclusive events, giving you an example, right? Flipping a coin and getting a heads, that's one event. Flipping a coin and getting a tails is another event. Can they happen at the same time? No, right? You might have a coin that takes its time before it lands, but eventually it lands on one or the other. So those would be examples of two disjoint events. Now there are other things. For example, if I have a deck of cards, we'll talk more about this in future videos, and I say I'm going to take out one of these cards. What is the probability that this card is a black king, right? Let me see. Well, it's definitely not. You can see it, okay? But in that case, it could both be a black card and it could be a king card. So that would be an example where there's overlap, right? So we have to take a look and see, do we have disjoint events or do we have overlap? Okay, so let's head back to our notes here where we were talking about what happens when you have two disjoint events. So if you do have two disjoint events, if you take the probability of the first event, like getting a heads, plus the probability of the second event, like getting a tails, when you add them up, what do you think their probability will always equal? Let's think about it. The probability of getting a heads, for example, plus the probability of getting a tails. I'll use H and T for short. Getting a head, theoretically, is 1/2, right? And getting a tails is also 1/2. And when you add up 1/2 plus 1/2, what do you get? 2 halves, or 1, also known as 100%. Okay, so yes, the probability when you add up two mutually exclusive or disjoint events should always equal 1. Well, why do we care about such a thing? Well, what if we want to find the probability that something does not occur? For example, if I tell you that the chance of rain tomorrow in my city is 30%, then what would the chance of it not raining be? You might already know the answer, 70%, right? Because the probability of not A is always 1 minus the probability of A, 1 minus 30%, because together, not raining and raining, their probabilities should add up to 1, or 100%. Okay, so stuff you already know, but we're just saying it formally here. What if, instead of talking about cards and instead of talking about dice and coins, what if we talk about marbles for a moment? So imagine here that you have a jar of marbles. And in this jar, or bag it says, in this bag, 4 of them are blue, 1 of them is red, and 3 of them are green. Let's find these theoretical probabilities. Now, the reason I insert the word theoretical is because we haven't done this in the past and then told you the results, right? I haven't told you that in the past I chose this many marbles and this many were red. And instead, I'm telling you the total that are in the bag, okay? So in theory now, you can calculate the probabilities. What is the probability of choosing a green one? Take a moment, pause the video, see if you can get all of these right. I bet you can. Well, you would say to yourself, how many total marbles are there? Because that's my denominator. 4 plus 1 is 5. 5 plus 3 is 8. So your denominator should have 8 possibilities, right? And for the favorable outcomes, that's how many of them are green, that would just be 3 over 8, okay? And again, feel free to change this to a decimal and to a percentage. But for now, for the sake of convenience, I'll leave it as a fraction. What about the second one? How did you do here? Probability of getting a blue or a green. Okay, now notice, are those mutually exclusive, right? Are they disjoint? Always think that through, kind of like our deck of card questions earlier. Can you be a blue marble and a green marble at the same time? Not according to the definition, right? Not here. Now, sometimes in real life we have blue-green colors, but here we're having distinct categories of blue and green being separate. So we have to follow the instructions they provide. So let's take a look. For blue or green, we would have probability total of 8 at the bottom. How many blue or green marbles are there? Well, if you said I need to add 4 plus 3 to get 7 out of 8 as my answer, you would be correct, okay? One of the things you're going to talk about, you'll see me talk about in a previous video, it might even be our next one, is the idea of or when you're dealing with probability. And that will always imply addition, okay? Or implies addition with a little twist, and we'll talk about that twist in a future video. But for now, since these are disjoint possibilities, blue or green being separate, all we had to do is add up the blue, add up the green. That became our numerator. Oh, here's a not example. We haven't had one of those yet. Probability of something not happening. So what's the probability that we do not get a red? Okay, do not get a red. Maybe you've played a game before and you're like, I just want to not land on, going to jail in Monopoly or something. So you're trying to find the probability that something does not happen. Well, you could add up all the possibilities, right? We could say, how many of them are not red? Well, we have 4 which are not red, because those are blue. We have 3 which are not red, okay? And so you could say that would be 4 plus 3, or 7. That's definitely a valid way to do the problem. But another way of doing it would have been 1 minus the probability of red. Now you might think that seems like a lot of work. I just prefer to do it the way I did it. Well, the reason this formula is helpful is if you had a lot of information, not just a few marbles in each category, but if you had several hundred or thousand, adding those up would take a lot of time. So if you instead just knew the probability of red is, in this case, 1 out of 8, right? Can you subtract that from 1 pretty easily? You can use your calculator if you have to, but I hope you don't. That's just 8 over 8 minus 1 over 8, or 7 over 8, right? Same answer. So that formula will become more important as we have more data, okay? So right now it didn't seem as necessary, but I promised you it'll be a lifesaver. So make sure that is in your notes. Probability of a purple marble. Is that even possible? According to what we have here in our bag, purple was not mentioned. So if you said 0 or 0 out of 8, which is still 0, you would be correct, okay? If on the other hand we say, what is the probability that you get a blue or a red or a green? Well, that's a guarantee, right? That would have been 1, right? So if something is certain, probability is 1. If something is impossible, probability is 0. Great job. Well, we have one more slide. Let's see if we can put this all to use. Pause the video and try this one on your own. So in this case, we have a nice die. A fair 6-sided die is rolled, and you want to find the probability of each of these. Now, this is theoretical again because they haven't given me any experimental data, okay? So in theory, what is the probability of getting an even number when I roll my die, okay? And again, this becomes more complex the more dice you have, right? 2 dice, it's a little more interesting. We'll talk about that in a future video. So for an even number, remember your options for a 6-sided die are 1, 2, 3, 4, 5, and 6, right? Those are your 6 options. So for our denominator, there are 6 possibilities. How many of those are even? Yep, 2, 4, 6. That would be 3 options. So again, reducing your fraction, you should say 1/2, right? Or 50% or 0.5, those are all the same. What about the next one? What did you get? The probability of not rolling a 1. Well, you could add up all the ones that are not a 1, or you could just say 1 minus the probability of a 1. What would that be? 1 minus 1 out of 6, because there's 1, 1, if you will. In other words, that's 6 over 6 minus 1 over 6, or 5 out of 6. Again, the formula wasn't as necessary here since we had a small data set. You could have simply added up all of these numbers, not the actual numbers on the die, but the number of them that there are. There are 5 numbers that are not 1, okay? The next one is a little interesting. Make sure you understand the difference between greater than symbols and greater than or equal to, right? Greater than, strictly, without the line underneath, is just saying bigger than. So it does not include 3 in this case. So we're saying, what is the probability of a number which is bigger than 3, greater than 3? Well, that would only be the 4, the 5, and the 6, wouldn't it? So that would be 3 options out of 6 again, or 1/2. Notice if I had said greater than or equal to 3, then we would have had a 4th option, so 4 out of 6, or 2/3. Very different answer. That's why you need to know the difference between greater than or equal to. This one includes that number, and the other one excludes it. It's just a boundary point, so it means beyond it, okay? Finally, what is the probability of rolling a 7? Now, we're not saying with 2 dice, we're saying with 1 die. Is that even possible? No. So that should be a 0. All right, so we've introduced in this video the very basics of empirical and theoretical probability. I hope that these definitions are starting to make some sense and that with practice you'll become an expert at this probability. If you have any questions, please reach out to me. Otherwise, happy practicing because math is not a spectator sport. I'll see you next time.